These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks. All right, so you want to take a blank piece of paper and maybe turn it horizontally, and then towards the left end, we'll start with the idea of force. That's okay. It'll still be a good review anyway to go through it. Okay. So let's start with this idea of force, close to the left end. Leave some space above and below. And when you're ready, remind me, what's the symbol for force?
F.
Capital F.
Capital.
Good. And what's the unit for force?
Newton.
All right. Then our next concept is work and energy. So what's the unit for work and energy?
The unit's joules.
Good. And then we want to draw an arrow between them and say what's the formula that relates the work and the energy?
Force equals...
I'm sorry, I should have been more specific. What's the formula that relates force and work? What's the formula that relates the force and the work?
So does it work equal force times something?
So we have some more space. Work equals force times distance. Now we know that generally speaking, the work tells you the change in the energy. So I'm writing work and energy next to each other. Sometimes these are kind of interchangeable, because if you know what the work that was done, you know what the energy is. Last semester we saw that technically we are only supposed to look at the component of the force and the direction of motion. But at this point, usually we don't have to worry about that. Work is just force times distance. Okay, now going on from that, we can go over the concept of power. So when you're ready, do you remember what the unit is for power?
Watt.
Good. Now notice I'm not using a W for a work or for watts because I don't want to confuse them, so I'm just going to spell those out. Now we need an equation that relates the work and the power.
So power equals... That relates work and power? So I think it was like work over seconds or something.
Equals
Power.
Okay, good. Power equals work. Now what concept is measured in seconds?
Time.
Time. So to be consistent, we should be working with concepts here and not units. So the power is the work over the time, but the work tells you the change in energy, so sometimes we can think of this as the power equals the energy over the time. So that means we should be able to figure out what a watt is. How can we break down a watt?
Joules over seconds.
So let's say that you've got a light bulb, a 100-watt light bulb. What does that mean?
So for 1 second, it has 100 joules of energy or work.
So we've seen in the past, a good way to deal with this is we know that a watt is a joule per second, and then it really is clearer if you put a number on the bottom, and the number we can put on the bottom is 1. So what does it mean if a light bulb is 100 watts? It means that if you run it for 1 second, it will use up 100 joules of energy. by doing 100 joules of work. If you use this bulb for 1 second, it'll do 100 joules of work and use 100 joules of energy. Now that might seem kind of useless because who uses the bulb for only 1 second, but suppose you used it for 3 seconds, how much work would it do?
300.
So this is actually very useful. If you know how much energy it'll use up in 1 second, it's easy to figure out how much energy it'll use in any particular amount of time. In fact, you can see that from this equation. Work is power times time. We just were doing that right here. If the power is 100 and you use it for 3 seconds, 100 times 3 would be the work. So it's actually very useful to know the power. So what does the power tell you in words? It tells you the rate that you're using energy. The rate that you're doing work is the rate that you're using energy because you're using energy to do the work. So again, the work and energy are kind of interchangeable here. So the power tells us the rate that we're using energy measured by the time. So this is a very, as we talked about last time, this is a unit of much practical importance because you have to pay the power company for all this energy. So what does it mean if you have a 60-watt light bulb?
For running 1 second, it uses 60 watts of energy.
It does what?
60 joules of energy.
Yeah, if you used it for 1 second, it would use 60 joules of energy. Well, what's the downside of that? Well, it's not going to be as bright. What's the upside? You only have to pay for 60 joules of energy. All right, so that's the trade-off. So this is a practical unit. Okay, so that's our power. That's important enough that's good to have in your head and not have to look up, but here we have it. Okay, now, building on top of the power, we have the intensity. So we need an equation that relates intensity and power. I don't know if you remember that one, do you? I don't know. What's the equation that relates the intensity of the power?
Is it power by time? Or does that do with area?
Yeah, not really time because we've already taken the time into account. Yeah, the next thing to take into account is the area. Okay. We need a symbol for intensity.
The S?
Yeah. Now, actually, sometimes people use I, and sometimes people use capital S. I would be more logical, because I for intensity, but maybe people don't like to use I because we're also using I for current. So in your textbook, they sometimes use S for intensity. So you might see either of these for intensity over here. So writing our equation, I guess I'll use I for intensity, but again, sometimes your textbook would call it S. Intensity, so what would be our formula then? If we know the power, how do we find the intensity? You're on the right track with the area.
Is it power times?
Turns out that it's the power over the area. So I could just as well have said S equals power over area. Okay.
And then with unit watts, it would be more squared.
Yeah, we should definitely think about that. So there's no special name for the unit for intensity, but we can say it must be power over area, watts per meter squared. So let's say that we're designing solar panels. That was the example we used last time, so the good trusty solar panels. And how well will the solar panels work? Well, it depends on how intense the light is that's hitting them. So let's say that the solar panels are getting hit with a light. I'll just make up a number, intensity of 150. Let's make an intensity of 7. So this is probably very low for light, or I don't know. I have no idea what the intensity of sunlight is. No idea at all, but I'll make up the number 7. I have no idea if this is way too big or way too small. So 7 watts per square meter. How would we interpret that?
So for 1 meter squared, there's 7 watts of power.
Yes. So remember, we're making a solar panel, and what this tells us, again, it's easiest to interpret a ratio if we put a 1 on the bottom. What this tells us is, if we make a solar panel that's 1 square meter in area, it's going to absorb 7 watts of power. If we make a solar panel that's 1 square meter in area, it'll absorb 7 watts of power. Why is that of interest? Well, that means that that will run a 7-watt light bulb. So this is not very effective to just have the one square meter anyway, because 1 square meter here can only run a 7-watt light bulb, basically. If we had an intensity of 100 watts per square meter, then that would mean that a single square meter of solar panel would be absorbing enough power to run a 100-watt light bulb, assuming that there was no energy loss, everything's efficient. Okay, so that's the meaning. Now again, you might wonder, well, who the heck cares about 1 square meter? You're never going to do exactly 1 square meter, but suppose that you actually decided to build 3 square meters. How much power would that absorb?
3 square meters would absorb
21 watts. So again, knowing how much power 1 square meter will absorb is actually all it takes to figure out how much power any amount would absorb. What we just did here is we just solved this equation for power. We said the power is the intensity times the area. We just said, well, if you have an area of 3 square meters, 7 times 3 is 21. We just did that from the units, but you can see that from the formula too. That's what you usually have to do on the test. It would be too easy to just plug in power and area and find intensity. Usually they tell you the area and the intensity, and you have to find the power.